Hello students, welcome to Focus Math Plus. This is our fourth session of Chapter 3, The World of Numbers. The first session, we discussed questions from exercise 3.1, which were based on natural numbers and whole numbers. In our session 2, we discussed questions from exercise 3.2, which were based on integers. In our session 3, we discussed questions from exercise 3.3, which were based on operations on rational numbers. And in this session, we are going to discuss how to plot rational numbers on a number line and also discuss questions from exercise 3.4. So let's get started. Before we discuss the questions from exercise 3.4, it is important that we recap what are rational numbers. So according to the definition, rational numbers are numbers that can be written in a form of a fraction p over q, where p is the numerator and q is the denominator, and provided that q is not equal to 0. So the denominator shouldn't be equal to 0. It could be 7/11 and not 7 over 0 because this is undefined. So hence the denominator shouldn't be a 0. And that's the condition for any number being a rational number. We can see examples like natural numbers. All natural numbers are rational numbers. All whole numbers are rational numbers. All the integers also come under the groups of rational numbers. Fractions, both positive and negative, they also come under the group of rational numbers. And the decimals which are terminating are also under the rational number category. Now, what are terminating decimals? Terminating decimals could be expressed as, now suppose if you're going to divide the number 7 by 5, 5 divides 7 just once. 5 times 1 is 5, and when you subtract you get a 2. You can continue dividing by adding a decimal point and a 0 here, and you could see that 5 divides 20 4 times. 5 times 4 is 20, and when you subtract you get a 0. So we get the remainder as 0. So when you divide and if the decimal terminates and the remainder is 0, so these kind of decimals are called as terminating decimals. And also decimals which are non-terminating but repeating. You could observe a pattern here. 0.333. Here it is 1.6666. 6 repeats. Here the digits 2, 7 repeats. 27. And here the digits 1, 2 repeats. So we see a pattern. Here 4, 5, 6, 4, 5, 6, it repeats. So here the three digits repeat. So we see a pattern. We observe a pattern in these numbers. When you see the three dots, which means that they are non-terminating, which means non-ending. But they are repeating. The decimals repeat. The pattern repeat. So non-terminating and repeating decimals are also rational numbers. Mixed numbers are also rational numbers. What are mixed numbers? They are called as mixed numbers because it comprises of a whole number as well as a fraction. So together it makes a mixed number. So all the negative numbers, decimals, all of these, they come under the rational number category, and also the number 0. Now, let's see how rational numbers are represented on a number line. We know how integers are being represented on a number line. We have done that earlier. Suppose if you were to mark the point number 3 on the number line, -3, you know that it is 3 units towards the left of the origin. And if you were to plot the point 4 on the number line, it is 4 units to the right of the origin, which is 0. It is towards the right. So that's pretty easy. But if you have to plot a rational number, what should be done? Yes, of course, rational numbers also could be represented on a number line. And just the fact that these rational numbers will appear between two integers. Now you see, for example, this rational number 1 over 2 is between 0 and 1. The rational number -3/4 is between the two integers 0 and -1. So these rational numbers will appear between any two integers. Now let's discuss how the rational numbers are represented on the number line. The first fraction, 1/5. Because the denominator is 5, the interval 0 to 1 is being divided into 5 equal parts. So we can divide this interval from 0 to 1 into 5 equal parts by drawing 4 lines. 1, 2, 3, 4. So these four lines divide this interval into five equal parts. 1, 2, 3, 4, 5. And this first line represents 1/5 of the fraction. This represents 2/5 of the fraction. This one represents 3/5 of the fraction. This is 4/5. And the last one is 5/5. Because any number divided by the same number gives you 1. So we write it as 1. If we were to mark this point on this number line, since because we need 1/5 and 1/5 is here, so this is how it has been plotted. Let's look at another fraction, fraction 3/4. This is also a proper fraction because the numerator 3 is smaller than the denominator 4, and hence q is 4. We have to divide the number line into four equal parts. The interval 0 to 1 is being divided into four equal parts. First, second, third, and the fourth. So this first one is being represented as 1/4. This is 2/4. This is 3/4. And this is 4/4, which is 1. Because 4 divided by 4 gives you 1. And now since because you have to mark the point 3/4, 3/4 is marked here. Let's look at another fraction, the fraction 6/7. This is also a proper fraction and the denominator is 7. So it has to be divided into 7 equal parts because q is 7, the denominator. So the interval should be divided into 7 equal parts. So the interval would be from 0 to 1. Since because this is a proper fraction, this will lie between 0 and 1. And this has to be divided into 7 equal parts. For that reason, you have to draw 6 lines. 1, 2, 3, 4, 5, and 6. 6 lines have to be drawn in order to divide this interval into 7 equal parts. 1, 2, 3, 4, 5, 6, and 7. And hence the first one represents 1/7. This is 2/7. This is 3/7. This is 4/7. This is 5/7. This is 6/7. And the last one is 7/7, which is 1. And we have to mark this point 6/7 on this number line. And it is marked here 6/7. So 6 part of the total 7 parts. The next fraction is an improper fraction, 3/2. This could be written as a mixed number. So when we divide 3 by 2, 2 divides 3 just once. 2 times 1 is 2, and when you subtract, you get the remainder as 1. The quotient is also 1. So it could be written as 1/2, 1 whole and a half of it. So let's see how do we represent this on a number line. Since because this is an improper fraction, it is converted to a mixed number, so it has 1 whole. So the intervals will be from 0 to 1. You'll have 0 to 1, so that's one entire whole interval and a half of it. Since because the denominator is 2, we divide them into two equal parts. Each interval is divided into two equal parts, and there's another half of this interval, which is 1.5. So this is represented as 3/2, which is 1/2, and as a decimal, it is 1.5, 1 whole and a half of it. I hope the plotting of rational numbers on a number line is clear. So here are a few important topics that we need to remember. The first thing is the definition of rational numbers, that a rational number, it can be represented as a fraction p/q, where p and q are integers and q is not equal to 0. Here integers means that they aren't decimals. The next thing, absolute value of a rational number. Absolute value is actually the distance of a number from the origin or from the center 0, and hence because the distances are in 0, the absolute value of any number is always positive. The next is the density of rational numbers. So there exist many rational numbers between any two given rational numbers. Now let's look at these in detail. Absolute value of rational numbers. Since because absolute values are the distance of any point from the center 0, so these are representing distances and hence they can't be negative, and they are written within this symbol. Absolute value of 5 is 5. Absolute value of -5 is also positive 5. Absolute value of a positive fraction 4/3 is 4/3. Absolute value of a negative fraction 4 thirds is also a positive fraction 4 over 3. And absolute value of 0 is 0. And absolute value of any decimal which is positive or negative, the answer is always a non-negative number. So you have to remember that these values could never be negative. It is always positive because it determines the distance from the center to that point. Next, the density of rational numbers. Between any two rational numbers, no matter how close they are, there's always another rational number. And there are many ways to find out the numbers that lie between those two numbers. Now, let's take, for example, the numbers 1 and 2. These are also rational numbers. They are also natural, they are also whole, and they are also integers, and they are also rational. So we can keep finding more rational number by taking their averages. How do we calculate the average? We add the numbers and we divide by the number of values, isn't it? So since because we are adding 1 and 2, 1 plus 2 is 3. Since because we are adding two numbers, we are dividing this by 2. 3 over 2 is 1.5. So we also got a fraction and a decimal as well. So these are also rational numbers. Hence, we were successful in finding a number between 1 and 2. Now let's continue this. Now, since because we are starting with 1 and we also have the fraction 3 over 2, now let's try to find out a number between both of these numbers. So let's calculate their averages. We have seen in the previous video how do we sum up the rational numbers. 1 could be represented as a fraction as 1 over 1, and we can then make the denominators common by multiplying it by 2. And 2 times 1 is 2, and 2 plus 3 is 5. And in the denominator, we just copy the denominator, 5 over 2 divided by 2, because we are calculating the average. We are adding two numbers, and hence we are dividing these values by 2. 5 fourths, because 5 over 2, it is divided by 2. So this could be written as 5 over 2 times 1 over 2, because this 2 is written as a fraction as 2 over 1. How do we divide fractions? We do keep, change, flip. Keep the first fraction, change the division symbol to multiplication, and we flip the second fraction. So the reciprocal of 2 over 1 is 1 over 2. So multiply the numerators together and the denominators together. So you shall be getting it as 5 fourths. 5 times 1 and 2 times 2, 5 fourths, and hence we found another rational number between the numbers 1 and 3 over 2. Now let's carry forward from the number 3 to over 2 and to 2. We can also find out another rational number by calculating the averages. We do the same thing. We add these fractions and we divide them by 2, and we can find another rational number as 7 fourths. And we can just keep doing this forever and ever, and we can always find another rational number. Hence, no matter how close two rational numbers are, there's always another rational number between them. Now let's discuss the questions from exercise 3.4. The first question is, represent the rational numbers 2 thirds, which is a proper fraction, negative 5 fourths, which is a negative improper fraction, and the mixed number 1.5 on a single number line. So we have to write the decimal versions of these numbers, and we can do it by dividing. 2 thirds is a proper fraction, and if you divide 2 by 3, 3 doesn't divide 2, so you just add a decimal point and add a 0 as well. 3 divides 20 6 times. 3 times 6 is 18. When you subtract, you get the remainder as 2. We can still keep dividing by adding zeros. 3 divides 20 6 times again, so that gives you 18. When you subtract, you get a 2. So you can just keep repeating this process, and you are going to get the same answer each time. So this is a non-terminating and a repeating decimal, and hence they are rational numbers. So this is 0.666. So you can understand that this number 2 thirds is going to lie between the interval 0 and 1, hence because it is a proper fraction. The next number 5 fourths, which is a negative fraction as well, negative 5 fourths, we can divide 5 by 4. 4 divides 5 just once. 4 times 1 is 4. When you subtract, you get a 1. You can keep continuing dividing by adding a decimal point and a 0. 4 divides 10 twice. 4 times 2 is 8, and when you subtract, you get a 2. And then you can add another 0, and you can divide this by 5. 4 times 5 is 20, and the remainder is 0. Hence, this is a terminating decimal. which is 1.25. So this is going to be somewhere between 1 and 2 because this is 1.25. So this is going to lie between the interval 1 and 2, but you have to be careful that this is a negative fraction, hence these values are to be represented as negative values. The next thing is going to be the fraction 1/2. So this is a mixed number by itself. While you look at it, it is 1 whole and a half. So it's 1.5. So on the number line, you can plot these values 0.666. This is a positive decimal, so it's somewhere beyond 0.5. It's here. And the next 1.5, this is also on the positive side of the x-axis, one entire whole and a half. And then we have the negative fraction, 1.25, which is one entire whole and a quarter. So this is where it is marked, but you have to be careful since because it is a negative fraction, it is marked on the negative side of the axis. I hope that's clear. Let's discuss the question 2 of this exercise. The question says find out three distinct rational numbers that lie strictly between -1/2 and 1/4. So we have two fractions over here, of which one fraction is negative and the other is positive. My main perspective is to see that these fractions are having the common denominator. To have a common denominator, I just need to multiply these fractions by some number. But I would rather prefer having a larger denominator so that I get a lot of rational numbers between them. So I choose to get the denominator as 8 in both of these fractions. So what should I multiply with 2? It is 4. And also I should multiply the numerator by 4. And what should I multiply by 4 to get a 8? It is 2. 4 times 2 is 8, and I have to also multiply the numerator as well. So when you do this, you get -4/8 because this is a negative fraction, and the second fraction is now 2/8 because 1 times 2 is 2 and 4 times 2 is 8. And now I have both of these fractions. I have to find out three distinct rational numbers. Distinct means it has to be all different and not the same. So on the number line, you can just mark these values like -4/8, -3/8, -2/8, -1/8 on the left side of the origin, and then we can have 0 in the middle, and then we can have 1/8, 2/8, 3/8, 4/8, and so on. So since because we have these two fractions, -4/8 and 2/8, I just have to pick any three distinct rational numbers. So I can choose -3/8, and -2/8, -1/8. I can also choose 0, or I can also choose 1a. So any of these three, because we are just asked three, it can be any of these. Okay, it doesn't matter if the denominator is different or same, but just that it has to be between both of these rational numbers and they all have to be different. I hope the question is clear. Next question. On the third question, we have been given two fractions. One is negative and the other is positive. We have to add both of these fractions. But since because we see that one fraction is negative, this is eventually turning up to a subtraction problem. So how could we add or subtract fractions? To add or subtract fractions, we need to have common denominators. So we have to find out the LCM of 4 and 12. So the LCM of 4 and 12 is 12. So what should I multiply with the first fraction? I have to multiply the first fraction by 3 so that I get the denominator as 12. 4 times 3 is 12 and 1 times 3 is 3. Since because this fraction is negative, this is negative. Now I can add these. Since because I have a negative fraction and a positive fraction, adding a negative number with a positive eventually is going to be resulting in a subtraction problem. So I'm going to subtract 3 from 5, which gives me a positive 2. Remember, 3 negatives and I have 5 positives. Each negative cancels a positive, and I'm left with two positives. So 2 over 12, which could be simplified by 2, as the common factor is 2. 2 divided by 2 is 1 and 12 divided by 2 is 6. So the answer is 1/6. Fourth question of exercise 3.4. A tailor has 15 3/4 meter of fine silk. If making one kurta requires 2 and 1/4 meter of silk, exactly how many kurtas can he make? So you have to think about what operation should be done. This is the entire length that he has, and it requires just 2 and 1/4 meter to make one kurta. So you have to estimate like how many kurtas would he be able to make in this given amount. So which means that this is going to be turning up into a division problem. So you have to divide 15 3/4 must be divided by 2 and 1/4. But first, we have to convert these mixed numbers to improper fractions. 15, 3/4. So how do we convert? We multiply 4 with 15. 4 times 15 is 60, and we then add the 3. We go clockwise direction. We first multiply and then we add. 15 times 4 is 60, plus 3 gives us 63. So that's 63 over 4. The next mixed number, 2 and 1/4. 4 times 2 is 8, plus 1, it is 9. So that's going to be 9/4. So these mixed numbers are now 63 over 4 divided by 9/4. How do we divide fractions? So there is a strategy to divide fractions, which is keep, change, flip, which means we keep the first fraction 63 over 4 as such, and we change the division symbol to multiplication symbol. And then we flip the second fraction, which means we write the reciprocal of this fraction, which is 4 nines. So 4 will take the place of the 9 and 9 will take the place of the 4. And we can then just multiply and we can simplify as required. So while you do this, you can see that 9 divides 63 7 times, because 9 times 7 is 63, and 4 could be divided 4 times 1. So 4 divides 4 once. And so the answer is a whole number, which is 7. So 7 is the answer, which means that 7 kurtas can be made from these many meters of fine silk. Next question, and the last question of this exercise 3.4. Find three rational numbers between the decimals given. So it's actually very easy when we deal about decimals. 3.1415, and we have the decimal 3.1416. So we just have to go according to the place value, right? So if you write 3.1415, this 3 is in the ones place, this is in the tens place, and 4 is in the hundreds, and then so on. We can just add an extra decimal here. And from this point we start and we have to go to 3.1416. So you can just keep adding additional values, like it could be written as 1, and then the next decimal could be 3.14152. The next one could be 3.14153. So you could see, by increasing the place value, we can just write as many as decimals as possible. So since, because you're just to write three rational numbers, these are enough. 14151, 14152, 14153, and hence you can write infinite number of rational numbers between any two given rational numbers, because rational numbers are dense. You can just keep writing numbers forever. Now let's look into the last question of this exercise 3.4, which is question number 6. Can you think of the other ways to find a rational number between any two rational numbers? The one method that we looked into earlier was the average method, wherein we add two numbers and we divide them by 2 to find out the number between them. Let's say, for instance, the fraction 3/4 and the fraction 5/8. If you are to find out the rational number between them, you have to find out its average. To do that, you have to add both of these rational numbers. As such, we can't add them because the denominators are different. So we can create a common denominator by multiplying the first fraction by 2. 3 times 2 is 6, 4 times 2, 8. And then we have 5/8. When you add this, you get 11/8. And you then have to divide this fraction by 2. And this whole number 2 could be written as a fraction as 2 over 1. So it is division of the fractions 11/8 and 2 over 1. And when we divide fractions, we use the strategy keep, change, flip. We keep the first fraction, we change the division symbol to multiplication, and we flip the second fraction. So 2 over 1 is written as 1 over 2. And that's going to result into 11 times 1, which is 11, and 8 times 2, which is 16. So this is yet another rational number between them. So if you just keep continuing with any two rational numbers, you find out its average, you can generate infinite number of rational numbers. And you can also write equivalent fractions to generate rational numbers. And with that, we come to the end of this exercise. And thanks for watching.